Hi guys, this is a power supply we looked at some time ago actually, and a couple of people requested when we're going to do the next part of this repair, so here you are guys. I do listen, see. So yeah, what's happened with this is initially it wouldn't power up. Yeah, I'll link the original video, it's quite long, but basically we have a chip at the back here on this board that effectively monitors the current and voltage on all the outputs, yeah? And this chip, via these two opto-isolators here, let me just zoom down a bit, you can see them better. Go to there, go. Okay, so this chip, via these two opto-isolators, control the pulse width modulator controllers on a little PCB that fits here. And this is the one, CM6800. This chip is a combined pulse width modulator for the output stage, which is two transistors on here, and it's also a PFC controller, power factor correction controller, which controls the device on this board here, which is basically two FETs in parallel, and the diode, so it controls and drives these, and this is your PFC. So basically the PFC boosts up the incoming voltage to about 375 volts DC, and then these switching transistors run from that voltage, which is obviously charged in this capacitor, and generate the output. On the previous repair video, if I can just find the information, I've kept it on one side. This is the actual controller chip, which is the one back on here. And we did some reverse engineering on this, and what figured out was basically that the two opto-isolators, one of them switches the pulse width modulator on and off, the CM6800, and the other one is a feedback that effectively tells it to generate more or less output. So that's basically how far we got with it last time. So anyway, with a bit of messing around, I actually managed to get it to power up. And once it powered up, I switched off the light bulbs in series. I took the light bulb out of circuit because it was upsetting the PFC, and powered it up without, and it powered on and run for just a few seconds, but all the output voltages were low, and then it just went off, and it turned out that one of the two MOSFETs in the PFC had gone short, just one of them, not the other one. It didn't go bang, it did blow the fuse, but it just quietly went short. So that's as far as we got, so this is where we're going to carry on from. Now I'll give you a bit of a background. I mean, obviously the best thing would be to watch the original video, but we can have a look. So this is a controller chip. I ordered some more of these, so I've got some of those here, and this is the heatsink with the power FETs on in the PFC circuit, and one of these, I think it was this one, a short circuit. Just switch it on. No, it's not that one, it's the other one. That one's okay, and channel MOSFET. The other one, just go to the other one. Okay, and the other one's short. It's short between all the pins, if you look where these are on the board, basically the two devices are in parallel. So effectively, the gate and the drain and the source, you can quite clearly see they're connected together, and I'm sure that the two gates were basically connected together as well. Let's have a look on resistance range. So if you look at the gate, which is here and here, they read 40 ohms. There's a little resistor in the circuit here, it's 20 ohms, There's another little resistor in the circuit here, which is 20 ohms. I think this side of them, basically connected together, they are connected together. So these are in parallel, they just both have a little resistor in the gate drive. And that's basically to stop any imbalance, like when they turn on, if they don't turn on at exactly the same voltage, yeah, because the two gates are not exactly connected together, they're just connected together via low resistances, and that's normal. So that's where we've got to. So what I need to do now, and we will just check, but I know I checked it before, this is the diode and the PFC circuit, yeah. And this was okay. Yeah, diode junction. Fine. So I'm going to change this MOSFET. I'm going to change the controller because the controller is connected to the gate of these, and when this went short, because it's short to all the pins including the gate, it might have damaged this. So we'll change that as well. Just before we do that, let's just have a bit of a reminder of what a PFC circuit actually looks like, yeah, if you've not seen one before, so you understand what we actually have here that we're trying to repair. So the PFC is basically like this. You have AC coming in, yeah, 220 volts here, AC, going into a bridge rectifier, which I won't bother to draw the 4 diodes, but it is 4 diodes, yeah. And these are the AC inputs, and coming out of the bridge rectifier, plus and minus, yeah. The minus goes to hot ground, yeah. This is what's called hot ground. It's effectively floating at half mains potential, or rather it's all of the mains potential half the time, because each half cycle either live or neutral is connected to this alternately on the half cycles of the sine wave, yeah. That's why you can't put your oscilloscope on it, by the way, or a grounded oscilloscope I should say, yeah. From the positive, normally in a normal circuit across here you would have a big smoothing capacitor, yeah, and that would charge up to about 300 volts, something like that, yeah. The way the PFC works, you have a coil, inductor coil like this, yeah, and from the inductor coil you have a MOSFET going to ground, and this MOSFET switches on and off very rapidly, very high frequency. So basically when it switches on, it draws current into the inductor, yeah, starts the inductor flowing, okay. An inductor is kind of like a water wheel, so imagine a water wheel, yeah, paddles, yeah. If you try to sort of get water to flow through the water wheel, initially nothing happens, yeah. So you got water coming in here and water going out here, yeah. When the water first comes in, this has to start moving. It has inertia, yeah, and it needs force of the water to start moving. Until it moves, nothing comes out. This is roughly how this inductor works. It has electrical inertia, so you draw current in, the current flows in here, but it doesn't flow through it. What it does is it magnetizes the coil, yeah. Once the current starts flowing, imagine the water wheel starts to turn and some current's coming out through here, yeah. What happens is then you switch this off, and the water wheel, if you like, keeps on rotating. It's like free running, yeah. You can't just stop under its own weight. It keeps on running, yeah, and that's what gives the boost voltage. And basically you have a diode here, and this is your main smoothing capacitor or capacitors across here, yeah. And coming out of here is about 375 to 400 volts, okay. And that's a typical circuit. Usually there's actually another diode from here to here, yeah. So that's basically how the circuit looks. So this has a controller, yeah, driving the gate, and in our case, as I've just shown you, we've actually got another MOSFET, yeah, connected across the first one in parallel, yeah, with a gate, and there's a little 20 ohm resistor here, there's another 20 ohm resistor here, yeah, and they both go to controller, and that's basically what we have. Sorry, it's a bit messy, but you can see where it is, yeah. So what's happened with ours, one of these has gone short but the other one hasn't, and that's unusual. If there's some sort of short or overload, like it's turned on for too long, you'd expect them both to go short, most likely. I'm not saying it couldn't, but it seems so, yeah. It's also possible there's some sort of problem with the load down here as well. So the factory is working too hard to try to generate the boost voltage. But whatever caused it to blow, we'll have to have a look, yeah. So what we're going to do is we're going to replace the controller chip, yeah, CM6800, and we're going to replace the FET, and the FET, I can tell you now, or 18N50. Yeah. So I'm now going to replace these with some supposedly fake components from AliExpress, and let's see if the supposedly fake components actually work. Yeah, let's give it a go. Here's the original one that I've desoldered. I don't know if it is faulty, but I'm suspicious it might be because of the short circuit on that power MOSFET, yeah, from the high voltage to the gate. But yeah, that's the original one, and this is our AliExpress one, so we could say it's a copy of that. Yeah, you might think it's a copy of that. Doesn't necessarily mean it won't work. I mean, my opinion is, honestly, why fake these sort of components? Because it's cheap. They're not like something that's like highly sought after and in big demand and short supply. So I don't actually see the economical gain of faking them. But anyway, let's some people believe that. In my experience, things work almost always. So let's see. So we've done that, yeah. Now let's get on to changing these MOSFETs. What I have come across, though, I will say, a couple of times with AliExpress, MOSFETs that the source and the drain are the wrong way round, as opposed to like the data sheet, or as opposed to the one that's in the circuit. And I've seen that on a couple of times when I've been repairing amplifiers, and interestingly, in both cases, when I kind of like got the thing to fit, like reverse the two pins, it actually worked, and the amplifier actually worked, yeah. So I don't know what was going on with that, but let's have a quick look at our good one. Let's just see which way round they are. This is something I do always check when I order MOSFETs, and actually not necessarily from AliExpress. On one occasion they came from eBay. Actually in the UK they were eBay, and I had that problem where the pinout didn't match. So let's have a look at this one. Okay, so pinout. So red is drain and green is source, yeah. So we can see that the drain is in the middle, yeah. So let's see. Let's have a look at ours. Yeah. Put the same way around. Blue, red, green, yeah. Let's have a look at it. So remember, drain, source, gate, yeah. Okay, that matches. So the pin out's the same, yeah. You can say that much, and it checked okay. Actually, another thing, let's just have a quick look and read the gate threshold voltage, the other parameters. It's just interesting to see how similar this is to that, yeah. So 4.29 volts. That's all it tells us, yeah, 4.29 volts. What's this one read? Is it close? I'm not sure this will tell us much, but it's interesting, yeah. It's interesting. 3.39, quite a lot lower here. Does that mean it's fake? Let's have a look at another one. Again, my opinion is that these are such commonplace components. They're not really cheap anyway. It's not like faking something that's valuable, like a GPU BGA or something like that. Yeah, I can kind of get that, but I don't get it for just stuff like this. Or maybe like rare transistors that are used in power amplifiers, and they sought after, yeah. Okay, so that's what they read. So let's replace both of them. Although one's checking okay, I think because of what happened to the one, I'm going to replace them both. Now let's put this together and see what happens. I've got it all put back together again. I'm just going to power this up. I've not got anything attached to the 24-way, so I don't want the power supply to start at the moment, apart from the standby. Yeah. So we'll connect the voltmeter to standby rail, so we can see what's going on there. And I'm interested to see, what happens now, having changed those components. I've got the 60 watt and the 100 watt light bulb in series, the two of them together, so effectively this can draw up to 160 watts and no more. Okay. Purple wire. Okay, we have that. In fact, if I just go to resistance mode, I'll know if I've got a good connection. Actually, it reads open circuit, just interestingly. Let's try it. Okay. Yeah, I'm sure I'm down there, resistance range. Okay, wants to read open circuit. Let's try it. So, well, interestingly enough, there's a bit of voltage there. I don't know how there's any voltage there, because this has not been plugged in at all. Yeah, but there's obviously a bit of charge in the capacitor. And it's been lying around for weeks, couple of months or more, before this was last switched on, I think. Okay, well, apart from we can't see the meter, it's there, yeah. So let's switch this on with our light bulbs in the circuit, so it can't actually go bang. I mean, the light bulbs might come on, yeah. Let's see what it actually does now. Okay, so the light bulbs flashed and have gone out, and we got 5 volts, yeah. That's a good sign. I'll switch it off, and I'll just check the voltage on the big capacitor. That should be about 375 volts. I'm just going to give it a little moment to discharge, and then we'll do that. It's been off for a couple of minutes now. I've just flicked it over. You can see, by the way, that the big smoothing capacitor is holding a high voltage on this, yeah, 210 volts still. So this is obviously quite capable of holding a dangerous voltage for a long time. Best way to discharge that is to use a power resistor. This is a 3.3k 5 watt power resistor, and what I'm going to do is I'm going to take the pair of pliers and just hold this across the capacitor to discharge it. Yeah. So I'm keeping my hands away from the metal on here, yeah, and we're just going to actually discharge the capacitor by resting the resistor across it. Oops, almost slipped with it. Go again. Probably best to go that way. Yeah. Okay, so we just put this across the big capacitor and hold it there for a minute or two. Some seconds. That should have discharged a lot of it now. Okay, let's see what's in it now, yeah. Well, it still has 130 volts in, yeah. This can hold a good charge for a good long length of time. I mean, obviously a lower value resistor would discharge it quicker, but then the resistor will also get hotter, yeah. So it's kind of like a mixture between how long it takes and how kind it is to the capacitor, yeah. I mean, you can short it with a screwdriver, but make a flash and a bang, and it doesn't do the capacitor any good whatsoever, or for that matter, your screwdriver, yeah. Okay, let's go again. Yeah, okay, so now it's basically discharged, yeah, 0.64 volts, okay, so that's safe. Having done that, I'm now going to power it back up again and just see what I've actually got across this. If the PFC circuit's running, which it may well not be at the moment because the main output isn't running, I should have like 375 volts here, but because the controller on this controls both the PFC and the main supply together, I'm not quite sure if the PFC comes on when the main supply isn't on, if you see what I mean. Okay, so let's try it anyway. So we'll plug the power back in. Get rid of the resistor for a moment, don't need that on the bench. Power switched on, again you can just see the light bulbs, so you should see these kind of like just flash ones, yeah. I can hardly Yeah, you can see it. Okay. So again, the light bulb should just come on just the once as it powers up. There you go. Yeah. Now let's see what's on this big capacitor. Okay. Here. To here. 317 volts. Other way around actually. Negative to positive. So I'd say the PFC is actually not running at the moment. All that's happening is when I showed you that circuit, is effectively from the bridge rectifier, these diodes are just conducting, yeah, and charging the capacitor. It was about 375. If the MOSFET was running, it'd be much higher. I've now put the analyzer on, yeah, so this should actually start the power supply. Again, I'm connecting to the light bulbs, so this should actually power up and the PFC should power up. Let's see what it actually wants to do now. Oh, sorry, one switch not switched on, that's why nothing happened. I'm a little bit ahead of myself, yeah. I've unplugged it. I wonder why nothing actually happened then. Okay, so switch that on, and let's just power it up. What do the light bulbs do now? Power supplies. It's trying to run. It's trying to run now, but it's not running. There's no light on the analyzer. I can hear it bleeping, there's some voltage there. What we got across here now? Lower, yeah. Discharging. That's strange. It's like something's given up the ghost here. You see, this is dropping, and I've got mains power on. Oh, I'll tell you what's happened. It's the bloody switch on the thing. Yeah, that's it. Now what we got? 320 volts. So, although the analyzer's faintly lit up and bleeping, the power supply isn't running, the PFC isn't running for sure. Yeah. 317 volts, not running. Let's have a quick look, see what we've got in the outputs, just out of interest. It's not enough to power this up. There is obviously some voltage present. Let's go black. And this needs about 2 volts or so. It'll power up because I've modified it. Yeah. That's interesting because there's 5 volts standby, so this should power up. What's under the voltages? Nothing on there. Nothing on there. Nothing on there. That's fun. I'm just a bit of a loss to explain why that's doing that at the moment. Purple. Purple. One of the blacks. About 5 volt standby. This should be on. I'll switch it off. Let all discharge again. That's fun. I'm not quite sure what that's doing at the moment and why this isn't coming on. I've got 5 volt standby. It should do, yeah. Okay, well we have to discharge these big capacitors again. Power's off. Off. Disconnected. You can probably still hear this bleeping, yeah. Discharge this. Yeah. Okay, that's discharged. This is only reading the low voltage, but I'm sure if I now that was long enough, just go across the big capacitor again. And what do we have? 1.3 volts. Okay, that's fun. I'm not really quite sure why that did that at the moment. I'll have a quick think about that. This is basically back to the original problem then. I've just plugged the analyzer onto my bench power supply and that's working fine. So yeah, the original problem we had with this is the main power rails wouldn't start. And then I'd only been measuring around the opto-isolators and for some reason they just started to start, and that's when it did power up and when it popped its PFC, yeah. So I think we're back to the original problem basically. We have to trace that through because I have no explanation if you saw the other video of why I actually did get it to power up. Yeah, obviously this behaves differently because previously this would only power up when I had 12 volts present. Yeah, and since I first looked at this I've modified this so this is acting differently. Okay, so let's have a look and we see trace through again, or I'll just check through the old video and have a quick look and figure out how this activation was actually working. Basically one of these opto-isolators needs to turn on to turn the power onto the circuit board, and there's a little 15 volt regulator under here somewhere that was involved in that. I've just familiarised myself then with this from last time I looked at it. I don't know why the ATX analyzer isn't coming on. I mean, this is modified to power up even if there's only 5 volt standby, and it does. I mean, I've had this on many other power supplies with just 5 volt standby and it comes on. Yeah, I've just tested again on my own good power supply. It's working. I'm a bit unsure. It was acting like the voltage was too low, but I measure 5 volt standby, so I'm a bit yeah, one of them. But that's not my main worry at the moment. So basically this is what we have. This chip here, this is the CM6800, yeah, CM6800. This is the pulse width modulator and also the powers of PFC. Yeah, I have part of the data sheet here, and VCC pin 13. This is the power input. This chip doesn't have an enable pin. Yeah, so the way the power supply switches this on when you've ground the green wire is it sends a signal from this part of the circuit somewhere, I haven't traced where it is, to the opto-isolator, yeah, and it turns this transistor on. This is your TNY279. This is the 5 volt standby. That's that device I showed you which has 7 pins, yeah. And basically this circuit here is an input. The power doesn't come from here. The power comes in from here through a high value resistor basically. So the power actually comes in here on this circuit then. So this powers up this TNY279 that generates the 5 volt standby. This also puts power to here, yeah, this transistor. But this transistor is normally switched off so it doesn't go any further than that, yeah. What should happen is basically the opto-isolator, this goes back to the low voltage side of the circuit, and when you power on the main ATX, you know, say you grab the green wire, you press the start button, it lights this LED up inside the opto-isolator which turns this transistor on. Turning this on then drops the voltage on the base, sorry, yes, on the base here, yeah. This is a PNP transistor, so this turns on. And the power comes through to here. This is a 15 volt fixed voltage regulator, so it comes through here. This might be say 25-30 volts, I can't remember exactly what it was. This drops it to 15 volts and this powers up the CM6800. So that's, once that's powered up, this then drives the pulse width modulator and the PFC. And where we got to last time, I was trying to trace what was happening here because this was switched off and this wasn't lit, and at some point it just started to work. Yeah, I must have an intermittent connection somewhere. It started to work, and when it started to work it ran for some seconds, and eventually one of the MOSFETs in the PFC just died. It didn't go bang, it just died. Yeah, so that's where we're up to. So we need to trace this again. At least we did a lot of the work last time, so we should find this is not lit up. Yeah, there's no voltage getting to here, yeah, so there's nothing coming out, and that's what I'm expecting to find now. So let's zoom down a little bit and let's have a look. Yeah, okay, this voltage regulator, the 78L15, the 15 volt regulator, is actually here, these 3 pins, yeah, 1, 2, 3. This one is the output. You can see quite clearly that goes to pin 1, yeah, on the little board that has the 6800. Yeah, I've actually marked it here, so I've shown the output of that goes to pin 1 that represents the little row of pins we have there, yeah, vertically if you like, yeah, that's that there. So it's on pin 1. So that's the output. The input to the regulator actually comes in at the other end here, yeah, and this is a little transistor that switches that voltage on. So what we're going to do is first we'll measure from negative over here to this end of this regulator. I'm expecting to find nothing, and the reason I'm finding nothing is because this opto-isolator isn't turned on. So I'm expecting then to go here pins 1 and 2, and I'll find less than sort of like 1.5 volts, I reckon, for an opto-isolator, yeah. So let's go to the voltage range. We're all connected to switch on. I'm connected via the light bulbs to make sure everything stays safe and nothing wants to go bang, yeah. So we'll just, and I need to connect the analyzer to activate the output, to ground the green wire, yeah. So we'll do that as well. Okay. So if you watch the part 1 video, this is basically where I got to, at which point it just sort of started to work before it stopped working, yeah. It started to work for a very short period of time. Damn thing's changed. It's just the wire bent over. You'll hear it bleeping anyway. So okay, let's just switch this on now. We'll see what happens. So the bulb's flashed once, yeah. Thing's bleeping. So if we go from minus here to our regulator, 15 volt regulator, this is the input, and there's nothing there, yeah. So obviously there's nothing coming out, okay. And the reason there's nothing there is this transistor, this is the input to the transistor, has 16 volts, yeah, coming in, but the transistor's switched off. There's nothing on the, well, the base and the emitter are the same, 16, so it's switched off, yeah. The reason that's switched off is this opto-isolator here doesn't have enough voltage on it, like 1.3. It says massive, but I believe it's the wrong way around. 1.3 seems to be not enough to turn that regulator on. Yeah, sorry, to turn that opto-isolator on, yeah. So the reason this is not working, it sounds like the original problem. Just showing you what I was doing. So basically, I know PNP transistors kind of confuse some people, yeah. But for a PNP transistor to switch on, the base voltage needs to be lower than the emitter, yeah. In which case we had about 16.05 here, 16.05, whatever it was exactly the same here, yeah. And the reason they're exactly the same here is because this resistor is holding the base to the same voltage as the emitter, and this photo transistor is switched off. So it's like this doesn't exist, yeah. So effectively this just holds the base up and it stays off, and that's what we have. And I had a look on here, I mean this one here, yeah, I had a look here and I've got 1.3 volts across here, but that appears to be not enough to illuminate the LED, or the opto-isolator isn't working, yeah. So let's have a quick look. One way we might be able to determine that is just if we go to diode mode. I'm not sure if this will actually do it. I've discharged the main capacitor and switched everything off, by the way. If I go to diode mode and look at this LED, if I measure the, oh sorry, press the button. If I measure the forward voltage drop of the LED, that might be the wrong way round. Let's go the other way. Yeah, it's only about 0.9. This is the other one. There's two of these. There's two of these, and they both effectively are the same type of opto-isolator. Yeah. This one's reading 0.5, 0.6, 0.9. They don't seem to read the same. But I'm sure, I know, I already took these opto-isolators off the board and tested them, and they were okay, yeah. They were okay, but I'm going to have to either take these off and test them again, and I should be able to measure the voltage across this it requires to turn on. I think that's the easiest way to do it. So let's take this opto-isolator back off the board again, and let's see what voltage it requires to actually turn on. The best way to test opto-isolators, I believe, is on a bit of breadboard like this, yeah. So I've got this connected to a variable power supply, and I've got 2 meters. And I'll just show you how it's actually connected up. Yeah, it's like this. So this is my power supply coming in plus and minus. This is the variable power supply. I've got 1 meter connected here in volts, yeah. So I've got a 470 ohm resistor through the LED and the opto-isolator, positive to negative. And this is where the voltmeter is attached, yeah. And on the other side, phototransistor, I've just got a meter in diode mode, positive to the collector, negative to the emitter. Because when it's in diode mode, it provides power itself, effectively measures the voltage drop across here, yeah. So that's how it's all connected up. So you can see this is the meter which is connected across the power supply. So this is on volts, it's actually on millivolts range, yeah. This is the meter that's connected to the transistor, and I need to put this into diode mode, which on this meter you have to press the button until it blips twice, yeah. It says VDC, that's in diode mode now. So that's set up, ready to go. So what we can do is now, I can increase the voltage coming from the bench power supply, you see here, yeah. It's still in millivolts at the moment, so that's like 0.13 of a volt, yeah. 0.2 of a volt nearly, yeah. And you can see at the moment that nothing's happening, the transistor is switched off, yeah. And we keep it increasing, so we're almost on a volt now. Just over a volt. And now you'll see, this is just starting to turn on at this point, yeah. But I want to increase it till this properly turns on and the meter will go bleep when it does. There, suddenly, yeah. So 1.06 on the LED, that's pretty much turned on. I'll turn it off again. Yeah, so suddenly goes, yeah. Now we had 1.13 in circuit across here. Yeah, we measured 1.13, and at this point you can see this transistor is fully turned on. Yeah, and that's a good LED opto-isolator. In fact, you'll find if I increase the voltage a bit more, it can't really go. That's as far as it can go. Yeah. But really, at that 1.13, it's switched on. Okay. Let's have a look at the other opto-isolator. So we'll just switch the power off. Take this one off here. We can put the other one on. I'm not sure which was which, by the way, but it doesn't matter. They're both the same. That way around. Okay. So there's the other one. Again, no voltage coming in. It's off. Let's just increase the power. Voltage. So just over a volt now. And it starts to turn on. Yeah, by 1.13 it's really fully on now, yeah. It can go a little bit higher than that, but that's it. At 1.17 it really is conducting, yeah. Okay, so that's how you can test an opto-isolator. But we can say 1.13 is enough to turn it on. So that isn't what the problem is. We've obviously got a problem somewhere else. So let's have a look at our circuit again. During that test, by the way, the value of this resistor isn't critical. I tried again with a 10k resistor here, and all that happens is you have to get much more voltage here to turn it on. So the voltage here still reads 1.3, but this ends about 12 volts by the time you've turned it on. Whereas if you use a 470 ohm resistor, this is just like a couple of volts or so, yeah. So that isn't critical. But anyway, I've put the opto-isolators back in the circuit. Let's have a quick look again on these two. The other one, by the way, oh, it didn't, it's my finger. It's switched off. Something stuck in me, made me jump. The other opto-isolator, by the way, is controlling the power this is generating. It's like it's throttling it forwards or backwards once it's running. That's what controls the output voltages. This is the one that switches that thing on, yeah. So again, we're all connected up via the light bulbs once again, just to make sure nothing nasty happens. And they flashed and it's bleeping, yeah. So let's have a look at these two opto-isolators. Now, this one I'm expecting to be switched off. And that one reads basically 0 volts, yeah. This one should be switched on. Now for some reason it's not reading 0.1, 1.3, it's reading differently. That's switched off now, yeah, that's switched off. And I just have standby. This power supply has some intermittent problem. It's like it sort of comes and goes, yeah. Let me see if I can trace where this power comes from and work a little bit way further back through the circuit, yeah. Those of you with sharp eyes will notice a moment ago I did actually get a reading on the meter of 1.4 volts across the opto-isolator LED. And if you were really sharp-eyed, you'll notice with the red lead to pin 1, which is the anode, the positive end of the opto-isolator LED, I actually read minus 1.4. Now I'm going to measure the voltage a different way now and get a different result, and afterwards I will explain to you what's going on here, because it could be very confusing to some people. Okay, let's continue. Right, had a quick look. It's switched on now, bleeping away, yeah. This is ground. So I haven't done anything, but I've now got 5 volts on here, yeah. This 5 volts, this is the top end of the LED, yeah, the positive end of the LED. This 5 volts comes from here, which is actually a 470 ohm resistor. Another end goes to here, yeah, which is a power pin going to this controller board. If you follow that round, it comes back down from here, yeah, and this is the 5 volt standby. That's the purple wire, yeah. So that's where that goes back to, 5 volt standby, yeah. So this resistor's got 5 volts on one end and the other end's 5 volts. And the reason it's 5 volts is because this LED is now switched off, even though I read 1.3 across it before like it was switched on. This end's 0.46, yeah, 4.6. And this end's 5. So that's only 0.4 across the LED. So the LED is off. So we found out that whatever switches this LED on is switching the negative supply. It's like ground in the other end of it, yeah. So we need to trace that to see where it goes to, probably a transistor somewhere. So let's have a look to see where that actually goes. Okay, so the key to this strange conundrum is the fact that the power supply is floating. The ATX power supply that I'm working on is connected to the mains on my workbench via an isolation transformer. This means there's no earth, no ground, it's just a floating potential. Which also means that if I touch any part of that circuit, that point I touch immediately becomes ground, and the other end, if you like, floats. So if I touch the live, yeah, the live would suddenly become neutral because it's grounded, because that's what neutral is, and the neutral would suddenly become live, and I wouldn't get a shock. Yeah, that's why. So this may not affect everybody, you know, on your workbench. This may not affect you, but I do want to show you the side effect that causes, and that's the answer to this problem. Yeah. So on the bench here I have an LED with a 470 ohm resistor that's slightly out of focus. Yeah, there you go. And I have it connected to just, you know, a 5 volt power supply, which is floating, a wall wart, if you like. Yeah, I think the Americans call these things. Okay, so if I connect the power now to this LED, obviously it will light up. So there it is. I've connected the power and it's lit up. Yeah, and as you would expect, if we get the voltmeter and we measure across the power coming in, we've got 5 volts for our power pack. Yeah, and if we measure across the LED, we'll have enough power to turn the LED on, which in this case is 1.9 volts, yeah, and the LED is lit up. And across the LED, I'm reading 1.9, yeah, simple as that. Now watch what happens if I disconnect the power, yeah. So I'm going to take the power off, sorry, wrong wire, not this one. I'll tell you what this wire is doing in a minute. I'll now take the power off, yeah. Where are we? White wire, power off, okay. This green wire is going nowhere, by the way, and the reason I've got it tagged on there is to simulate a PCB track, yeah, on the board. Now let's measure the voltage across our LED, yeah. So positive to negative, what's our LED say? In this case it says minus 4.5 volts. which is dropping a little bit, yeah, as I have the meter on. It's now saying minus. The other one was saying minus 1.4. This is saying minus 4.1. Yeah. The reason it's doing that is quite simple. This bit of wire here is acting as a RF radio frequency antenna. Yeah, and because the end of this is no longer grounded, the positive end is literally just floating now, so the positive's connected. There's no return path, which is actually the problem on our power supply, which is why the optical isolator doesn't power on. Yeah, it means I'm picking up just stray RF frequencies, and the LED is a diode, a light emitting diode. And what does a diode do? It rectifies. So it's rectifying the stray home, mains home, RF home, my mobile phone transmissions, and God knows what. Yeah, and that's why it does it. So I've mentioned that now. Hope that explains why we have that very strange reading. Yeah, and you can understand now. Just by chance on our power supply, it read 1.37, which is just about the right voltage for LED. Yeah. Okay, I knew it's reading 4 point something. If I'd seen that, I would have known straight away what was happening. Okay, there you go, guys. So let's continue with the repair now, and I hope that sort of cleared your brain as to what was going on. It doesn't actually go to a transistor, and now I come to think about it, I probably had 5 volts on here all the time, because I measured the voltage across the LED. I didn't measure from ground to this point, and I had 1.3 like it was switched on, but it still wasn't working. So where does the negative end of this LED go? Well, I figured it out. I know on this circuit board at the back here, I have a chip on the WT7525, this thing, but they come in various versions, and that was the N161, which is a 16 pin version. And this shows us a typical data sheet, but for the 14 pin. So I've had to effectively look up on the rest of the data sheet. Here it gives us all the signal names, yeah, and from the signal names I worked out which pins were on the 161 version. That's from this, yeah. So putting the signal names and this together, I could work this out, and this is what effectively we have. So our LED is this application is very much like ours. So this is the LED in the opto-isolator, yeah. One end goes to 5 volt standby through a resistor, which happens to be 470 ohm, and the other end connects to here, yeah, on this chip. We have 5 volts here, but 4.6 here, because effectively this needs to ground to turn this on. And this signal FPOB, if you look at the part of the data sheet, is a fault protection output pin. So this fault protection effectively is what turns the power supply on when there isn't a fault, basically, if you like. That should be low and it's high. Yeah. This one on pin 3, sorry, pin 4, yeah, this is pin 3. PS on button, it's the power supply on button, yeah. And this should be grounded. When this goes to ground, if there's no faults, this should go to ground and it switches on. That's how it works, yeah. And everything else on here are various current sense and voltage sense, yeah. And the power supply good signal coming from the power supply, yeah. So that's another interesting thing to look at. Actually, no, sorry, the power output good, that comes from the motherboard as well, yeah. That's an output, sorry, that's an output, ignore me. That's an output, yeah. So that's when it outputs power good back to the motherboard when it's all powered up, yeah. But we can ignore that. All these various inputs here and this one can affect this, whether it switches on or off. That's what I best figure out. So let's have a look at this. So we have we know we have 5 volts here, 5 volts here, 4.6 here. We can measure that. We can check this chip has got power supply on pin 15, yeah. And we can also check what's on pin 4, which should be low, yeah. So back to our little board now. I've kind of marked them. This is the VCC. This is the power supply for the chip, yeah. Should have 5 volts on it at least, okay. It is 5 volts actually. It should go from 5 volts standby. This one goes 5 volts to the LED and comes back there, which is the 4.6, and this is your power on effectively, yeah, your button. So what we'll do is now we'll power this up yet again. We're on voltage range. and you can see the voltmeter, and obviously the light bulb will flash again when I do this. Yeah, there it goes, powered up. Yeah, so let's check it. So this is the 5 volt standby. Oops, voltage range, that'd help. This is the 5 volt going to the LED, and we know the other side of the resistor is 5 volts. Yeah. Coming back from the LED is on this one, which is 4.5, so the LED isn't turned on. This is the power supply on button, which is low. Should be low, and it says it's 0. Yeah. This is power to the chip. And it looks like I don't have any power to the chip. What? Whatever supplies power to here is off. Yeah. That's a good reason for it not to be working. There's no power to the chip. Okay, let's trace that and see where that comes from. Okay. Oh, camera's frozen. 1 moment. Not sure how long that camera had been frozen. Hopefully it hadn't, because I've just kind of like restarted this, so maybe you didn't even notice. Okay, so this pin here, this does go to pin 15 of the chip. I can just get onto it via what looks like a diode junction, yeah, and that comes from the 12 volts over here, which seems rather strange place to come from, but that's where it appears to come from. Yeah, over here. But obviously there can't be any supply on the 12 volts, so it's not running. If we have a look from here, this is the 5 volt standby. That's the most likely place to expect it to come from. Then we go to pin 15 in diode mode. We kind of see like what is probably a diode there. So I'm guessing if we measure on pin 15 of the chip, which is here, this one, yeah, which is going to be difficult to do and show you, so you'll have to trust me on probing the right place. Yeah, with it switched on, we should see power getting to this chip. Yeah, 5 volts on pin 15. So once again, we start it back up and hope the camera doesn't freeze this time. No, it didn't. Look, you can still see me moving. Okay, so again we go to ground, and I'll just get onto the pin 15 on the chip itself on voltage range. Have we got any power to our chip? It's a bit difficult to get on 1 moment. Yeah, 4.47 was exactly what you expected coming through a diode. Yeah, I think we can assume that's enough to power the chip up. So it's got power. There's power on here. Yeah, we've got the power switch on low because it's attached to our little thing here. So that's correct. But it's not driving the LED. That's what it's doing. So what I need to do now is have a look at the data sheet for this and see if I can find any other reason why it wouldn't be working. So I'll have a look at that and I'll be back to you guys in a moment or 5. Okay, I've had a look then. So I mean basically you just got effectively 2 outputs. Yeah, you've got the fault protection one which switches the power supply on and off. It's like the enable switching. Well, it's sort of enabling the main power supply, you know, switching the 15 volt supply on via the opto-isolator. Yeah, and the other one is just power good output signal, which I haven't bothered to trace where it goes. All the rest are inputs. Yeah, now all these ones, apart from the power supply switch on the motherboard, obviously, the rest can only be active effectively when the voltage are present. Yeah, so they're over current and over voltage, under voltage for 3, 5 and 12 volt supplies. But they can't be there till the power supply is there, so I can't see that anything on those pins can affect whether this is working or not until it's working, if you see what I mean. I don't see anything here that would actually stop this from powering up. The power supply, you know, I said it goes to the 12 volts via a diode and the 5.5 volt standby. I had a look at the data sheet. It actually says that it can be between 4 volt supply and 20 volts. So obviously the 4.5, which is the 5 volt standby via the diode, starts it up, and then the 12 volt supply takes over. Yeah, so that seems normal. There's just this one, PGI, power good input. And I'm thinking, well, that maybe obviously enables or disables the whole thing, but that pin on the one I have, I had a look, down here, pin 1, it just goes through a capacitor to pin 2, which is ground, and I can't see any traces going from here to anywhere else. So I measured in resistance mode from here to all of these pins, and it's completely open circuit. The same in diode mode, and either polarity, you know, red and black on here. There's no connection from here to that, and I don't think it goes anywhere else but the capacitor to ground. So I'm guessing that can't stop it either. So the next thing then is to actually change this chip. I think I have some of the equivalent. I couldn't find this chip. I couldn't find the 161 version. I can only find the 14-pin version. But on bad caps, I looked up for the WT7525-161, sorry, N161 equivalents, and it came up with this one, which is a DWA 105, and that was on badcaps.net. Gave a list of various you know, equivalents of power supply supervisor chips. So that's the equivalent. So I'm going to put this on here and see whether it actually works now. Okay, I'll just interrupt this repair again, just to mention this. I'm sure a lot of you are aware of this, but this is a tutorial, yeah, so let's sure we do it right. So we have in this power supply this chip, yeah, the 7525, which is the power supply supervisor basically, yeah. There's some signals going on that are slightly confused, so I'll just tell you now what they are, yeah. On your power supply, basically coming out of your power supply when you first switch on, there's 5 volt standby, yeah, 5 volt standby. Going to the motherboard, yeah, MOBO, because I can't be bothered to write it out, motherboard, yeah. Your motherboard starts the power supply. When you press the button, it grounds the green wire, yeah. Sends a signal, PS on, yeah, power supply on. That's the green wire, yeah. 5 volt standby, this is the violet or purple wire, whatever you want to call it, yeah. Okay. Once it gets this supervisor chip then starts the main PSU, yeah. Out of here comes 5 volts, 12 volts, 3.3 volts, and minus 12 volts, yeah. Blue, orange, orange, yellow, red, yeah. That switches the power on, but what it also does then, this supervisor monitors this and sends a signal back. And this is that power OK that I said I haven't bothered tracing to see where it goes, yeah. Where it actually goes is down the grey wire. So this is a grey wire going back to your motherboard to say power OK, yeah. That's it. And then the PCH in here, SIO PCH, will monitor that and know power's OK and continue with the boot sequence. So if it didn't get that power OK signal, or not within a certain amount of time, it may well not boot, yeah. Once it sees that, it takes the reset off the CPU. Okay guys, just a little extra there, but hope that clarified, at least for maybe a few of you, what's going on here, yeah. Okay, let's carry on with the repair now. I've changed the chip then, so that's all soldered back together. I suppose all we can really do now is try again and see if that's made any difference to it. Something's changed because the light bulb's come on and stayed on. Yeah, you can see the reflection of it. The light bulb came on and stayed on. So something has changed here. And it shuts down much quicker now. But the power supply analyzer isn't reporting having the output voltages. And that's strange. Also, I noticed, by the way, only one of my light bulbs is actually working. I wonder if the 100 watt one's bulb's gone. Only the 60 watt lamp came on, this one didn't come on for some reason. I hope it doesn't fail, because it's getting a bit harder to get hold of these things. That's strange, because they're in parallel. I find that a little bit odd that one of them comes on and one of them doesn't come on. Okay, let's go again, and this time let's measure one of the output voltages on here. See what we've got here. So let's go to the 3.3. I might have to give it a bit of a load as well. Yeah, we've had this before. Well, it doesn't like to work at that load. Well, I still find strange this isn't actually lighting up, yeah. So let's give it a go again. So the light bulb came on and stayed on last time, and did the same. But I don't have any voltage coming out of it. I think we can assume now then that we've fixed this part of the problem, yeah. So if we look at this LED now, this will be the 5 volt, and I'll put the power in a moment. This will have the 5 volts, and then this lot should read lower, yeah. And the difference we expect to be at least 1.3 volts. So once again, power's on, yeah. 5 volts. 0.2, let's get to the end of the resistor. 1.3. And this end is basically ground. So I'd say that's obviously switching the power supply on now. Why not have any outputs coming from it? But I don't. But the thing's obviously drawing a lot more power now. So I'm sure the power supply is now running. If we go over to the, oh, I have to go from the high voltage ground, yeah, so you can see the test meter as well at the same time. And this is the regulator that feeds the power. This is awkward. It's rather. So from hot ground, this is the 15 volt supply to our chip pulse width modulator. We've now got it. And what have we got on the main capacitor? We've got 292. I'm sure that's higher than before. I'll have to check it. Still not sure if PFC is running properly. Okay, what I've done here is clearly fixed one fault on this power supply now. It now tries to power up, but I have another problem somewhere on this side of it. I mean, it could be that because this bulb's coming on bright, there's not enough voltage getting in this now. It might be the PFC is drawing quite a bit of power. This is only limited to like 60 watts, and I'm wondering if there's not enough. And the reason being, the light bulb's on bright, so that means the AC voltage getting to this is quite low, and yet there's 300 volts in here, which sort of tells you the PFC is actually working. Yeah. The other thing that me puzzled is why my wondered what bulb wasn't lighted up to give me like 160 watts, and turned out it was a faulty lamp bulb holder. You know, I checked the bulb and everything, and it's a bloody light bulb holder. So that's another equipment failure. Yeah, so I've now connected it back up with 160 watts in. The other thing that I'd be wondering was the fact that the 15 volt supply was only 13, like it can't generate enough power. I'm hoping that 160 watts is enough to stop this going bang if something goes wrong. Yeah, I mean that's like 240 volts is like well, about 0.6 of an amp actually, 0.66. Yeah. We got to try it, guys. Okay, so it's back on the bleeper thing. I'll put it so you can see it. I've now got hopefully both light bulbs in. And let's see what happens now, see if it actually powers up again, if something wants to go bang or not. Yeah, I'll just hide, by the way. Nah, okay, let's just switch it on and see what it does. And nothing happens. Oh, that switch, yeah, that switch. Shall we try it again? Are you ready for it? Are you ready for the excitement now? What's he going to do? Well, I only have one bulb bloody working. I've just put a new bulb holder on and made sure, you know. Let me have another look. Well, I've screwed the bulb back in a bit further and measured the resistance now. This was coming on pretty damn bright, like it's drawing a lot of power. So I'm not sure exactly what's going to happen here. I mean, there's no shorts on this that we know of. Yeah, we've looked for that sort of thing before. I mean, we can check. But I was convinced there was no shorts on this. Let's just go. There's not much voltage left in it. So all the power's off. It's unplugged. So I'll discharge the capacitor fully. Yeah. Okay, we discharged. We'll go. Make sure there's no voltage in that. No, that's gone now. Resistance from across the main bridge rectifier. It's high. I mean, there's no short there. It seems when the PFC is running, it's trying to draw a lot of power. Okay, let's give it another go. Let's see if we can get it to work, if we get something to just go pop, yeah? No, it doesn't like that. That's too much. That is too much, much too much, yeah? It stopped anything blowing up, but that is much too much. So there's something wrong on the high voltage side of this now. Well, it was obviously drawing a lot of power, so I've taken this light bulb back out. I've just got back down to the 60-watt bulb again, just to limit the power that can run into this thing. So let's switch it back on again, and let's see what it does now, yeah? Well, it's on, and it's bleeping, yeah? Now, the reason I'm sure the PFC is working is this. This is the AC coming in, yeah? AC mains. The bulb's on, so a lot of voltage dropped across there. And there's only about 8 or 9 volts AC coming into this, yeah? In fact, it's reading even less now. No, I'm reading the wrong place, sorry. There's about 6 volts AC coming in here, yeah, live to neutral, yeah? But if you go to the big capacitor, yeah? Onto DC, yeah, onto the big capacitor. It actually has 300 volts in it, 263 and climbing, yeah. So that tells me, and it tells you, the PFC is working. How do you think it's getting 260 volts in there when it only has like about 7, 8 volts? It's gradually increasing, yeah, because the thing's working. So that tells me the PFC actually works. Now this discharge is much faster now. Yeah, before there was nothing discharging it. Now it discharges quite a lot quicker, yeah. So something's drawing a bit of power from it. So the PFC is working, we're getting a high voltage to here, but it's not running, yeah. Right, stop bleeping now. It's not running. Yet, if I just discharge this capacitor, you'll see. Find my pair of pliers to do this safely, yeah. Come this way. Just discharge, I'll just take a few seconds and we'll have a safe voltage in this, yeah. That should do it. So we now have 0.3 of a volt, okay. So PFC is running, we can see that, we've got a high voltage here. And there's obviously no short across this, because we've got a high voltage in it, there can't be a short. So there can't be anything drawing excessive power from here, but it doesn't work. And the problem's obviously over this end somewhere. This is why I thought by putting the 100 watt in as well, to give it a little bit more, you know, current it can draw, this would draw up faster. You know, the voltage obviously would increase, that was the idea. And it's not doing that, so I think we've got some sort of problem in the PFC in a way, but the PFC is working, and that's why I'm quite confused. I can't just quite get head around exactly why this is doing what it's doing. So it's another day today, fresh morning, yeah. This is well, you see what this is doing, yeah. It powers up now, but it seems to have some sort of problem. It's drawing a lot of power, and it's not generating the main outputs, yeah. This doesn't run, even though it should run when 5 volts is going in, because I modified it and I've tested that, and yet it lights up and blips but doesn't give any reading, and I'm not quite sure why. And the PCH seems to be, I think, is what's taking a lot of power here, yeah. But it is charging the capacitor, it is boosting, so it is working in a sense. And when you switch off, the voltage on here takes some time to discharge, yeah. So it's not like something the main power supply is taking a lot of load from it either. So I need to kind of like break the cycle and try and figure out where the problem is. And I'm honest, I don't know what's wrong with this power supply. It's not a type of fault I'm familiar with. So I'll see what I can do, yeah. So it's one of these things like you go to bed and the next day you've got some ideas even though you weren't worried about it when you went to bed, yeah. And the first thing that occurs to me is to disable the PFC, and that's by removing the two MOSFETs, yeah. So effectively we'll still have the diodes. I can't just lay my hands on the circuit diagram I made, I'll find it, but so the diodes will still conduct from the bridge rectifier to the main capacitor, yeah, this thing, yeah, this. So if we remove these, that'll disable the PFC completely, but the power will still go through the coil and through the two diodes and charge the capacitor. And the power supply should then run if it's working. The PFC is only to improve efficiency, it's not essential, yeah. If it's got 300 volts in the capacitor, it should run. So let's disable the PFC by removing these MOSFETs, yeah, and see if that helps, or at least helps us to determine something, yeah. To those of you who are probably shouting out at the screen saying, Rich, you've got fake MOSFETs from AliExpress, what do you expect, yeah? That could be the case, but bear in mind, if you see the first video, and if you didn't, you should watch it. On the first video, at the end, when I effectively this decided to come on its own, yeah, so it's no charge, by the way, something sharp on it. When this decided to come on, it did the same thing. The light bulb came on, drew a lot of power. As soon as I decided to switch the light bulb off thinking it was a PFC, it then ran for a few seconds and it blew a MOSFET. So the same thing happened with the original MOSFETs, it seems to be doing now with the replacement ones, yeah. Okay, I mean, it may be fakes, but that doesn't explain what went on. The same thing happened before I put them in, yeah. Okay, let's continue. Let's get these MOSFETs off here and then let's see what it does. Okay, so that's the MOSFETs removed. I've put this back on, just put the diode back. I was actually just going to solder the diode straight to the board because, it's not working as a PFC anymore, it's just acting as a diode, and I'm not drawing any power from this. I didn't think it actually needed the heatsink, but it was so well stuck to the heatsink I decided it was easier to just put it back on that way, yeah. Okay, so we now have our power supply without any PFC, yeah. And I'm interested now to see, yeah, put it this way around. I'm interested now to see what happens if we power it up. So I'll just get the light bulbs and now let's see what it does. That's all connected up then, ready to go. So just a matter of putting the power on. I've taken the 100 watt bulb out, just the 60 watt. I'm expecting this to flash and go dim. That's what I expect it to do without the PFC. But let's see what actually happens now when you switch it on, yeah. Yeah. Flash and dim, and this is bleeping. Oh, it's trying to give me some display, but the main power supply isn't running, I think. So I think I've only got 5 volt standby. We can check that. So let's just check it on here. Just get hold of the thing out the this one tangled up here. Sorry. Okay, so we have 5 volt standby, but we don't have the other voltages, yeah. Nothing. I'm not 100% sure if that's the fact I've disabled the PFC, but I don't think so. We'll just check again, actually. I'll just power it back on and let's just make sure we still have a supply to the controller chip, yeah? And don't get your fingers too close, Richard. Alright. Okay, so let's have a look. So from ground here to the controller chip, yeah? Yeah, 13.2. 14.75. Okay. So that's still effectively powered up. This has over 300 volts in it, yeah. So this is acting like possibly the controller chip has some sort of problem which I've replaced, yeah. Okay, let it discharge and then let's see if we find another way to work on this. Okay, so I thought of another way, but it didn't help. I thought if I take my bench power supply, don't power this up from the mains, but just put the 15 volts on here. So this is powered up with 15 volts. That maybe the pulse width modulator and PFC would start to oscillate, and I can see some drive going out, you know, to the switching transistors, but that fact it doesn't do anything. So then I'd look at the data sheet, and I don't think it will work like that. I think it needs all the signals basically, which I'll mention in a minute. What I did also try, I thought, what's going on with my ATX analyzer? The fact is it's not powering up from the 5V standby. Yeah, this is the modification I made, and this is basically a boost converter, like a buck type thing, which is a boost. So it takes all the voltage coming in through diodes, so even the 3.3. This is supposed to work, so if you have 2.2 or more input, it'll give 12 volts output, and then that 12 volts effectively powers this. Yeah, and that's what this is doing, or what it should be doing, and it's not. I connected my bench power supply to the 5 volts and cracked the voltage up and found it's about 7 volts. This starts to work, and the output voltage is following the input voltage. It's not boosting anymore, so I can only assume that the little boost converter's packed up. In fact, I know that that's what's happened. This is stopped working, so I can fix that later. That's what's going wrong. At least that's nothing to do with this. Yeah, it worked on my other power supply. I proved it was working. Was that 12 volts? Okay, that's that one. Okay, so yeah, I'll tell you what else I think about this. We'll have a look at the data sheet. Yeah. So guys, I had another look to see if I can figure out what's wrong with this. I've had a good look at the data sheet, and I'm fairly convinced that if the PFC section isn't running, the pulse width modulator won't drive the main output stage either. They synchronize together, and there's something to do with the phase, where it's detecting the phase of the AC signal coming in, and it's determining when it's switching on the pulse width modulator basically. And I think because combined control, it's quite likely it won't work without this running. Yeah. So then I look at the data sheet. I just want to show you what I'm finding there. Let's have a quick look. I'll just go over to it one moment. In the data sheet then we have a typical application basically for this chip. Yeah. You can see basically this is the PFC circuit we're talking about. So this is the big coil, the diodes. Ours has another diode from here to here, which is quite common. And these are the two MOSFETs that are driving the output, which are actually wired in parallel. You can see, yeah, they're in parallel there. They're driven basically by these two transistors, one NPN and one PNP. And this is basically what we have on our board. I'll show you in a minute because I've checked them. I'll show you again that prove that these are actually okay. Yeah. This is the other drive, by the way. Similar setup, two transistors, NPN, PNP, and this is your main switching transistor. This is your main supply output. Yeah. Now there's some signals down here after the bridge rectifier before the PFC. This is like effectively rectified AC. Yeah, and it's monitoring these signals here. And this one current sense as well, and VRMS voltage sense. And I think that without the mains applied, because these signals are not there, it can't work, and I'm pretty confident that's the case. So anyway, our circuit turns out to be very similar to this, so let's just check all this to see if there is a problem. Yeah. These then you can see, these are the two transistors it shows in that typical application. This is the gate and this is the 22 ohm resistor. You can see it's coming to one of the transistors here, yeah, and the other transistor is here, and the other one I actually tracked it through from this resistor here. That goes up to here as well, yeah. So these are being driven from here, there's no doubt about that. You can see there's like a wire link that comes up here, yeah. And if you look at these two transistors, one should be an NPN and one should be a PNP, and we're assuming this is going to be the base, so we're not doing anything there. Let's go the other way around it. So if this is an NPN, this will now show a diode junction, and the diode junction. Just get onto it. Yeah, there you go. And the other one in the same polarity doesn't. But if we reverse them, it does, so it's a PNP transistor. Yeah, so we can be confident this is these two transistors, and this checks okay. There's two more down here, by the way, which drive the main switching transistors. I've checked them as well, and they're also okay. I've checked the 0 ohm resistors, I've checked all the resistors around here. You can see the drive comes from here, yeah, out of this. So I've checked that, and that looks okay. And because that looks okay, I'm kind of suspecting that it probably didn't blow the original chip, if you see what I mean. But the original chip had a problem, we had the same sort of problem, yeah. So I then had a quick look at the replacement chips as well. So what I have here, this is the original one that I took out, and these are two of the ones that I bought, yeah. And I started to have a bit of a look around these. So pin 10 is ground, so I can just show you on the first few pins of this one, for example, yeah. The third pin shows like a diode junction, yeah. But if you look on this one, this is the original one, it's pin 2 that shows the diode junction, yeah. It's not the same. This one's the same as the other replacement one, pin 3, yeah. So let's see if this is fitted to the shot nicely. Yeah, I went around the chip like this, and these are the voltages. We say voltages, these are what my meter says in volts on diode modes. So I'm going from black lead on ground, and I'm testing each one in turn, yeah. You can see this is what I'm seeing on the replacement chip, and the other replacement, although the values were a bit different, it would basically follow the same pattern, yeah. But on the one that was originally in there, this is what I'm seeing, yeah. So that's like the lower one there, and a lot of these show as being open. They don't, you know, you just don't read anything. I mean, they might on resistance mode, I haven't bothered to check, but there's obviously a big difference between this original chip and the replacement chips. And I don't know if the original chip was any good, because it basically had the same problem to start off with. So that brings me to a bit of a conundrum with this one now. So where I am with this one now, it's a bit difficult to continue with it. I don't know if the replacement chips are any good, or they fake, I don't know, but they certainly read different from the original one. But there again, maybe the original one was faulty, so I can't really determine anyway from this. I thought to put this one back in, but since I had this problem originally and blew the FET, I suspect that it's got a problem, yeah. I mean, that happened for a reason in the first place. I fixed the actual fault that we were tracing, yeah, that with the supervisor chip. It now switches this on every time. I don't know if the FETs are any good either, but again, the original one blew. So I'm kind of like reaching this point now where I need some more information. I need to know, are these chips any good? Are these FETs any good? Is there something else I'm missing? I mean, I appear to have checked out all the circuit round here, and I don't seem to have anything wrong. Oops, delivery, but that's toner for the printer. I needed that, yeah. Okay, so yeah, that's as much I can do with this, I think, at the moment. To go further, I think I need to order parts again from another supplier, but I'm hoping maybe somebody on here knows maybe something I've missed. There's one other possibility I will mention I can think of, yeah, but maybe if somebody knows, somebody has some of these who can measure the components like I've done with the diode mode, and let me, you know, tell me are any of them any good, yeah. The last possibility I can think of that would cause this to fail like this both times is if the inductor, the PFC inductor, has a shorted turn somewhere. So somewhere the enamel's scraped off, and somewhere on that inductor there's a short. That would effectively really destroy the impedance of this. So when the FETs turn on, it would magnetize very rapidly, yeah. And basically, because the FET is expecting this to be able to hold a certain amount of magnetism, it can't. It effectively becomes like a piece of wire very rapidly, and that's what would cause, you know, the FETs, you know, the light bulbs to light up brightly. Yeah, that's why that would definitely, a shorty turn in this would definitely cause too much current, and it would possibly still work, but work slowly or not very well. That's the only other possibility I can think of. Is that, yeah. Anyway, guys, let's see what you think. I'm very interested. And I've actually just shown you the wrong inductor because I got distracted. It's this inductor down here, this one, not that one. But the same thing, the shorty turn in that inductor would, it's the reactance or impedance would be very much hindered, and that would cause this sort of thing to happen, yeah, and blown FETs. Okay, guys, I don't know if you enjoyed that one or not, really, sorry. This is probably the first power supply I've looked at I couldn't actually fix at the moment. I believe I can, but I need some more information. Okay, see you soon, guys. Ciao for now.